All right, on last Thursday we started the analysis of failure, right? So like we said, so we want to understand failure. So we classify failure into two different kinds. We have static failure and we also have dynamic failure, right? So for dynamic failure, we know it's a little more complicated, and therefore we started with static failure. So there are lots of failure criteria we can use. The first one we did on Thursday is maximum shear stress, short for MSS, right? And we started with, we assume it's a shear stress inside of the component cause failure, because most of the time when failure happens, it's not perfect 90 degrees, it's 45 degrees. And from mechanics of materials, we know 45 degrees is where the maximum shear stress is applying at, right? That when theta equal to 45. So we did a bunch of analysis and it came up with, I apologize, I think I lost the notes. Anyways, luckily I uploaded that to the Blackboard, huh? Anyways, so we came up with this. We have an envelope which tells us if your stress is inside this envelope, there's no yield will happen, or in other words, no failure, right? Because the maximum shear stress is dealing with elastic material or ductile material, right? So yield is the criteria we look at when we're talking about failure. Okay, so if you have any stress state that's outside of this envelope, anywhere over here, then we say yield happens, right? Okay, so just a brief review of what we learned on last Thursday. So today we are going to move on to the second criteria we're going to focus on, which is called distortional energy. Alright, so both maximum shear stress and the ductile distortional energy theory is for ductile materials. So distortional energy believes the failure of a material is not caused by maximum shear stress, but instead is caused by distortional strain energy. All right. Per unit volume, which is bigger than maximum distortional energy. So, in other words, when you have a distortion energy stored in any of the element or any of the material, once you divide that by the unit volume, if it reaches certain maximum value, then failure will happen. All right. So what this criteria believe is failure. Of course, for ductile material, yield is a failure, right? Is related to angular distortion of the stressed element. So in other words, it believes extension or compression doesn't do any damage, but twisting it does. All right. So if you have distortion, because cause the material to have non-isotropic deformation, then failure will happen. All right. This is what I believe. Okay. So now let's see how we can analyze it. So we started with the arbitrary loading condition in a three-dimensional. For example, you have sigma 1, sigma 2, and sigma 3. Which one? Stressed element. Yes, stressed element. Alright, so we started with the arbitrary unit cell. We have sigma 1, 2, and 3 in 3 main axes, right? Only 3 normal stress, no shear stress considered, right? Okay, so we say this is it has a unit volume. Therefore, the volume equal to 1. And it's underloading a triaxial loading. Okay, let's say this is the case A. Very generic case, 3-dimensional loadings, and every single direction has different value. Right, sigma 1, 2, and 3, they're not equal to each other. Right. Okay, so that is going to be decomposed into 2 parts. I have sigma average, sigma average, sigma average on 3 axes, 1, 2, and 3 axes, right? Okay, plus whatever is the difference between them. Over here I have sigma 2 minus sigma average. Over here I have sigma 3 minus sigma average. Over here I have sigma 1 minus sigma average. Okay, all right, and here sigma average equals to the average stress of the total stress applied on the 3 axes, right? Okay. Over here, we can call this is a hydrostatic component. We call this is case B, and plus C is distortional component, which is component C, right? Now I say A is nothing just equal to B plus C. So I transfer arbitrary loading of 1, 2, 3 direction into 2 components. The first component is hydrostatic. Oh, if I sit here, can you guys see in the back? Should I say in the back, on the side a little? Or are you guys okay? Okay, all right. Okay, so this hydrostatic component tells you every single axis is the same, right? Goes to the average of the stress. 1, 2, 3 add together, divided by 3. So in this case, you are calling hydrostatic increase or decrease of the element, right? It's not going to cause any distortion. Well, whatever left, the difference between the stress and the average, we call it distortional component because they're different, right? Okay, so I say A equal to B plus C, which is right. Why? Let's for example take sigma 2 for example. Sigma 2, right? So whatever you have here, over here, let's use red. This stress, and this stress. So theoretically speaking, if I say the loading case A equal to B plus C, then of course whatever on the two axes, the stress over here should equal to this plus this, right? Okay, so you look at the left hand side is sigma 2, right hand side you have sigma average plus sigma 2 minus sigma average, which is also equal to sigma 2. Alright, so of course it's satisfied. So the reason why we do that is we want to transfer a very generic triaxial loading into 2 components, right? Because distortion energy believes this is a bad thing. This doesn't do any damage to the failure, but this is the component that will cause failure. All right, so we need to separate them, and then we focus on here. Okay. All right. Okay, so let's see here. Now remember, we discussed the concept of strain energy. The strain energy per unit volume for recall. Well, okay. All right, I'll try to write it a little slower. Strain energy per unit volume for a simple tension is equal to strain energy for unit volume of simple tension equals to this, right? That's what we discussed. Remember this? Did we discuss this? We didn't? You guys didn't cover this in mechanics and materials? Strain energy? No?
No, we skipped.
You sure?
Chapter 9 we skipped.
Okay. All right. A quick review then. Okay.
Oh, really?
Man, they don't teach you anything, huh?
Right towards the end.
Stress-strain relationship, right? So, what's a good way to start? Okay, so I just tell you the concept. So, strain energy is equal to 1/2 stress times strain, right? That's how much strain energy gets stored, right? The idea is behind this is like this. So, you know, there's a concept called bulletproof vest, and we know bulletproof vest. Did I say anything about this?
No.
I haven't? Okay. Man, I didn't teach you guys anything, huh? Alright. Apologize. We blame this on the new technology. I don't like to use iPad. Anyways, so, you know, for a stress-strain relationship for example, brittle material, stainless steel, it goes like this. Right? So we load it up, it broke. So this theta over here, tangent theta is equal to Young's modulus of any materials, right? This is how it's defined. Now this is a typical loading for brittle materials. Let's say this is stainless steel. Okay. All right. So we also know. Let me try to make this axis a little longer. Okay, so we also have a some material that has a lower Young's modulus. For example, polymer. Huh? Tangent theta equal to y? What's wrong about that? Huh? They what? Really? Well, first of all, you guys know stress strain, right? We know this, right? Okay. Yes? All right. And then we know for brittle material, you load up, you have linear relationship, and then you see non-linear happening, and the failure start to happen here, right?
Yes.
Okay, we're good on this page, right? Okay. All right. So, good. We also know for polymer or for plastic, for example, rubber band. Rubber band has really low Young's modulus because you can just stretch it with your hand, right? If if you have a stainless steel that's made out of some type of commercial stainless steel, but with the same shape of a rubber band, you can now stretch it, right? Use your hand. So for rubber band, it looks like this. Right, so this side over here, let's say this is theta prime, and tangent theta prime equals to y prime. This is my rubber band. And this is my stainless steel, okay? Alright, the concept of strain energy means the area underneath this stress and the strain curve. So, for example, this thing over here, let me use a highlighter, let's say orange. Okay, so whatever this orange, if you calculate the area, what we do, it's a triangle, right? So it's the area of stainless steel, SS, okay, that just equal to, since it's a triangle, equal to 1/2 whatever this stress over here is times whatever this strain here is, right? This is how you calculate the area. Agree? Triangle, right? Okay. Next, choose green. This is not what I'm asking for. Okay, so whatever inside this screen, the rubber band equal to similar. That's about equal to sigma prime, epsilon prime. Right. So this area underneath it is what? Is defined as strain energy. So therefore, the reason why I brought up a bulletproof vest up is because, you know, most of the time the bulletproof vest is made out of a material called Kevlar. Right, Kevlar is similar as this green area, right? Although it's a plastic, although it's a polymer material, but it has really high ultimate strain. Therefore, it takes more energy to break it. So the strain energy is a measure of how much energy it can store without failure. All right. Although for stainless steel or for other brittle material, they have high Young's modulus, but they have very limited ultimate strain. So this area underneath is the orange is way less than the yellow, right? So this is a concept of strain energy, and in other words, whenever you do a stress strain measurement, you can estimate how much energy has been stored inside there. All right. Now, if you're interested in, I can go a little more to details of the fundamentals of it, but I think it's not necessary. It's too complicated. So the only thing is try to remember this. Strain energy is defined by this. All right, 1/2 stress times strain. All right. Okay, so go back to the analysis. So when you have stress applied, then of course you are storing the energy into it, right? For a unit volume, like A. Therefore, this strain energy just equal to 1/2 stress strain plus stress and strain. Because energy, they don't have a energy is not vector, right? It's just a positive number, right? There's no negative energy here, right? Energy is always positive. So when you have 3 axes of loading, like this case, right? 3 axis loading. So each stress will cause its own strain energy because it's going to cause different displacement, right? Different strain. So the total strain energy stored in there is nothing but just a summation of these 3, right? Okay, so we also know when you have 3 axis loading, you have Poisson's ratio. Okay, so Poisson's ratio tells you when you have 3-dimensional loading, x, y, z, or 1, 2, 3, sigma epsilon x is not only a function of the stress applied in x, but in the same time, it's a function of the stress applied in the other 2 direction, right? We did mention this, right? There we. Okay, so when you stretch a rubber band, it's not only going to get extension on the direction where your force is applied, but it's also getting thinner, right? Okay.
Is that a V or?
Huh? Is it a what?
Poisson ratio?
Yeah.
Oh, yeah.
Yep. This is Poisson's ratio, right? Am I in the right classroom? All right. Okay, so if you have 1, 2, and a 3, this is what it looks like, right? That tells you you have 1, 2, and a 3 stress, right? So the strain in one direction is function of a stress applied in one direction, and also, of course, the stress applied in 2 and 3, right? The reason why here is negative is because when you have positive 2-direction stress, it's going to cause negative strain in the one direction because it's going to cause it thinner, right? It's going to make it thinner, so that's why it's negative. Okay, all right. Therefore, you plug this thing in it. So that this equation tells you strain is a function of stress applied. It's a function of a Poisson's ratio. It is also a function of Young's modulus, right? So I plug this equation back to here to get rid of all the strain components. Okay, so one, two, 2, 3, and 3, 1. Okay, so let's say this. This is 2. This is 1. So 2 into 1. This is what we have, right? Okay. So we'll leave this equation here for now. And the hydrostatic loading, which is case B, produces strain energy UV by substituting sigma average for 1, 2, and 3. All right, so what I'm trying to do is I'm trying to look at energy perspective, right? So see here, we agreed on this, right? We agreed on this, right? So case A equal to B plus C. I'm just decompose the stress into two parts. One hydrostatic, the other one is a distortional, right? Okay, now from energy perspective, whatever energy happening here should equal to the energy happened in here, right? Energy is conservative. I didn't create any new loading, or I didn't subtract any loading from it. So whatever the energy happening in here should equal to the energy B and C add together, right? Okay, so the strain energy of the hydrostatic loading is just equal to 3 sigma average divided by 2 E1 minus 2V, and recall the AV, average. Okay, if you want, I can make this AV as well, average. All right, so this is I'm looking at case B. Case B with where the average stress is defined, right? So we know the average stress is nothing but equal to 1, 2, and 3 divided by 3, right? So you can plug this thing into here, and you get your average stress caused strain energy equals to 1 minus 2V divided by 6E sigma 1, sigma 2, sigma 3, plus 2 sigma 1, sigma 2, plus 2 sigma 2, sigma 3, plus 2 sigma 3, sigma 1. Okay, so let's take a quick overview of it. We have strain energy of average. We have strain energy of the first case, right? So remember we said A equals to B plus C from stress point of view, right? Okay, but in the same time, what we're going to see is we have the strain energy we determined, which is U, and over here we have the strain energy determined average, right? And plus something we don't know, right? Yes?
Is that sigma 2 cubed? Yeah, that's what I was thinking too. That should be sigma 2 squared plus sigma 2 cubed.
Oh, that's right.
And then the one below it is like 2 sigma 2 2. Yeah.
1, 2, 2, 3, and a 3, 1.
That 2 just looks like the 1.
Where?
The one below it, in the line right below that.
Here?
Right there. 6. That's a 2. Okay.
Yeah. Okay, thank you. All right. So, like I mentioned, we're looking at energy perspective. All right. So, whatever the strain energy in case A should equal to the strain energy in B plus C. Right? Because I didn't add or distract any or subtract any force out of there. Right? So, therefore, this question mark should equal to U minus U average, right? Yes? Okay. Alright, this question mark, we give it a name. We call it distortional distortional energy, okay? Because it's distortional strain energy, and in short, we just call it a distortional energy. All right, so this distortional energy is equal to U minus UAV. And we know what is U and what is UAV, right? U is just equal to this, and U average is equal to this, right? And if you do the subtract of between these two, we should be able to calculate the distortional energy. Okay, so that let me do it a little better here. So let's say this is equation 3. This is my equation 4, and what we're doing here is plug in 4 and 3. So that equal to 1 over V divided by 3E sigma 1, 2, 2, 3, 3, 1 divided by 2. Okay, so this is what I have. Okay, now this is very important because it tells us what is the distortion energy caused by arbitrary loading in a unit cell, right? Okay, and one thing we can check is, let's see, what if you have average loading? Your three-dimensional loading are the same, right? You have 10 megapascal on the one axis, 10 megapascal on the two axis, and 10 megapascal on the three axis. Then let's see what is a distortion energy. Now, by definition, see here, if you have the same stress on three axes, this should equal to what? What should this equal to?
0.
All zeros, right? Because if you have 10 megapascal here, 10 megapascal here, and 10 megapascal here, what is the average? 10, right? 10 minus 10, 0. 10 minus 10, 0. 10 minus 10, 0. Right? So it should be 0. Okay. So let's see whether this distortional energy makes sense or not. If you have three things are the same, the distortional energy should be 0, right? Because there's no distortional stress applied. Once you plug it in, say, I'm just going right here. So this is 0, this is 0, this is 0. So that tells you distortional strain energy is 0 too. Makes sense. All right. So, and then we have a UD here. This D stands for distortional. All right. So, that's how we decided. Okay. Now, let's look at one extreme case as well. For what if we have only one axis loading? A single axis loading. For example, all you have is one direction, and all the other are 0, right? It's a very extreme case. Okay, so of course we know when you have a one-dimensional loading, it's the same as tensile loading, right? Now when tensile loading happens, we know it's only when tensile loading is equal to yield strength, then we say failure happens, because this is the definition of yield, right? It's only when the one-dimensional loading is high enough past its yield strength, then we say failure start to happen, right? Okay, all right. Now, let's plug it in to see what's the strain energy equal to. In this case, 2 and 3 are all 0. Okay, so this UD distortion energy in this extreme case, we give it a different name, UD prime. That is just equal to 1 plus V divided by 3E SY squared, right? All you need to do is plug in sigma 1 equal to SY, sigma 2 and 3 are 0 into this equation. All right? Sigma 1 is SY, 2 and 3 are all zeros. Okay? All right. Okay, and so why do we need to do that? So the reason is, you see, distortional belief is a distortional energy inside of the component cause failure, right? Now this is what? This is my baseline, right? That tells me when you have a distortion energy equal to 1 over V divided by 3 times SY squared, then this is minimum distortional energy you need to cause failure. Because when you have one-dimensional loading, the minimum stress you need is SY to cause failure, right? When you have a minimum stress equal to SY, we know yield start to happen. That's my failure point. And when you have a minimum stress applied over here, this is the amount of distortion energy stored in the material, right? So in other words, whenever you have your distortional energy that is equal or bigger than this UD prime here, then failure happens. Agree? Okay. All right. So all we did is we define what is distortional strain energy, and we also look at one extreme case, which is actually very simple, just one-dimensional loading, tensile loading, right? Although I only draw one, but you know there's two stress, otherwise it's not on the equilibrium, right? Okay, so that's that. And then if you do the comparison, let's see what's UD. UD equals to 1 over V, 1 plus V plus divided by 3E, 1V, 3E, this three, 1. Okay, so this is whatever on the left hand side. On the right hand side, is this, right? All I'm doing is just trying to plug it in. Okay, all right. So we see here's the coefficient which we can cancel it on both sides of this thing, right? Coefficient cancels out. Now most of the time we look into the reference, it's only going to give you a number for yield strength, SY, right? That's what you guys did for the project 1. I asked you guys to look at the tensile strength of the material that you choose, right? It's only going to give you one number. So what I'm going to do next is rewrite this equation a little. Get rid of the square. Instead, we have square root on the left hand side. Alright, so the stuff on the right hand side looks very familiar. We know what it is, right? What's SY? Yield strength. That's something you can find online. Okay, so the left hand side is whatever the distortional stress or distortional energy, we can calculate it, right? Okay, so therefore we'll give it a name for the left hand side of the equation. Looks familiar to you? That's when you use finite element for project 1. What's the number it gave you, right? So for a finite element, it's only going to tell you what's the von Mises stress. Now this is how von Mises stress is defined. For our project 1, we only did one-dimensional loading. So theoretically speaking, the von Mises stress sigma 2 and 3 are 0. Therefore, it's going to be the same as sigma 1, right? So see here, if this is non-zero and the 2 and the 3 are 0, this is the case we did for, let's say this is one direction, 2 and 3. This is 0, this is 0, right? This is what we did. Okay, so if we plug that in, you have sigma 1 squared plus sigma 1 squared divided by 2 square root. Of course, that's going to be sigma 1, right? So that is the definition of von Mises stress, and now we know how can we relate whatever we see in the finite element with a qualitative analysis we did here. All right? Yes.
I just have a question about all this that we've been doing for the past 2 lectures.
Yeah.
So there's no universal theory for failure.
Mm-hmm.
And these 2 theories that we've learned so far are just 2 theories for stress, right? For failure. How do you know which one to use?
How do you know? Okay, that's my next question.
We did the first one that had 3 cases, and now we're doing this one for distortion energy.
Uh-huh.
And then there's another one that's going to be the ductile coolant, right?
Right. DCM.
And those are for ductile
Right.
material. So how do you know which one to use?
Which one to use? That's actually what I'm going to discuss next.
Oh, I'm sorry.
Yeah. No problem. Yeah. So all we have been learning so far, mainly we'll focus on these 2, right? The other one, I don't think I've discussed it. It's they're complicated, not that useful. So all these 3 are for ductile material. And relatively speaking, the failure of ductile material is easier to predict. If it's brittle material, it's hard to predict, and I'm going to tell you why it's hard to predict. So what we're trying to see here is we're trying to have MSS and DE, and we know how do we quantify them. And then next, I'm going to tell you what's the relationship between these 2 and which one you need to choose. All right? Okay, so again, for maximum shear stress, we look at a 2D case, right? So we look at sigma A and sigma B. So we have 2-dimensional loadings, and we come up with something like this, right? This is what we did. Okay. What's going on? Earthquake? All right. Don't worry, we're together. All right. For 2D problem, let's see. Now we don't have earthquake here. We only have sandstorms, right? And it's not spring, so we're safe. Okay, so, huh? Yeah. Okay. All right, for 2D problem, because why we want to look at a 2D is because for maximum shear stress, we look at 2D problem, and we came up with this, right? So what we're trying to do now is we also look at 2D problem, and then we're trying to see how the distortion energy is going to show us, right? Okay, so for 2D problem, we say 1, 2 direction, they're just A and B. Sigma A, sigma B, sigma B, sigma A. Okay, and the 3 direction is 0, right? This is a perfect 2D case. Okay, now you plug it in. See, this is our criteria here. You should highlight it. This is our criteria here, right? So plug in sigma 1 is sigma A, sigma 2 is sigma B, sigma 3 is 0. try to plug it in. All right. Okay, so if you do that, then let's say this is sigma prime for 2D case. That is just equal to A minus AB plus B square root. All right, so this is what it looks like. Okay, now how do we relate them with maximum shear stress theory? Okay, so for maximum shear stress, we know we have sigma B as my y-axis, sigma A as my x-axis, and we did a bunch of testing, case 1, 2, and 3, and we came up with half of it, right? And we flipped AB order, and we came up with the other half. Okay, so what I'm trying to do is from here, how do we connect to here? Okay, all right, now again, like I said, sigma A is my x-axis, sigma B is my y-axis. So whatever on the left-hand side is similar as this, right? When you look at a Cartesian coordinate system, SY is just a number. It's going to give you a value, right? And what's inside here from a Cartesian coordinate point of view is just a ellipsoidal shape. You have your long axis, you have your short axis. That's the perfect example of ellipsoidal shape, right? Remember this equals to, for example, 10. That is an ellipsoidal shape, right? Now, if you have, if I remember right, if that, then it's equal to that. It's a perfect circle, right? So when the coefficient in the center is not equal to 2, then you have ellipsoidal shape. Therefore, you have a long axis and a short axis, right? Okay, so if you do that, you can combine these two together. So what you end up to be is like this. Okay, so again, SY, here SY, here minus SY, here also you have minus SY. Let me use the dotted line for maximum shear stress. So whatever here is maximum shear stress. Okay, now let's see how we put this thing into play. This thing, all right. So let me use the red. If you do that, if you do the ellipsoidal shape, okay, here. It's going to look like that. Oh, I didn't draw very good. It's the ellipsoidal shape right outside of the maximum shear stress box. Let me try to do it again. Alright, this is better. Anyways. Okay, so once you have that, then we can have some discussion. So there's 6 points actually they share together. 1, 2, 3, 4, 5, 6. These 6 points, they're on both maximum shear stress and distortion energy, which is easy to understand. For example, let's take this point A. For example, point A is nothing but a simple tensile case. Point A, you have sigma A equal to Sy at this point, right? So no matter whether you use maximum shear stress or distortion energy, when your stress is exceed the yield strength, then of course failure will happen, right? So therefore they're the same. Okay, now let's look at a special point. What if you have a point right here? A point right here. If you use, let's say this is my point B. At point B, if you use maximum shear stress, what does that tell you? Failure or non-failure? Failure, right? If you use distortion energy, what's it going to tell you? Failure or not failure? Non-failure, right? Of course. Because it's inside of the envelope, right? Okay, so by saying that, it tells you it's more conservative, right? And distortion energy is more aggressive, okay? All right, so now you ask me which one to choose. Depends on design. If you want to be more conservative, of course you use maximum shear stress. If you want to be a little aggressive in your design, you can use distortion energy. All right. Now, when you use a finite element, it's going to tell you the von Mises stress, right? So the von Mises stress is whatever on the left-hand side of this equation. All right. You can compare that with your yield strength. Actually, that's a perfect way of using distortion energy, right? Because this, whatever on the left-hand side, can be calculated using simulation, right? And you just compare that with the yield strength. If it passes that, failure is going to happen. If it's not going to pass that, everything will be fine, right? Therefore, using distortion energy, you can couple that with the finite element analysis you guys will be doing for the future projects. And about just let you know, so if we have two-dimensional loadings or even three-dimensional loadings, when you use von Mises stress, you know you're using distortion energy to judge the failure or no failure. Okay? Make sense?
Quick question, Dr. Lin. Is that x squared minus xy, y squared, is that supposed to be under a square root as well, or no?
This thing?
Yes.
Sure. Yeah, you can do this. You can do square on both sides. I mean, what I'm trying to say is this equation over here is a expression for ellipsoidal shape. All right, sy and sy squared, they're both constants. 10 and 100, they're both constants, right? So if you want to what's that word called? If you want to be more accurate, of course, if you do square, that ellipsoidal is just going to shrink a little, right? Because everything inside the ellipsoidal, the value will be square root of it instead of the full number. Okay, so it doesn't change the shape; it just changes the number. Make sense? All right.
So
Okay.
Should we write it or should we not write it?
Huh?
Should we write the square or should we not?
This is, I'm just trying to give you an example of what they are.
Just the shape.
All right, yeah. What you need to do is this equation over here. Now let's use this equation, right? This is what you need to focus on. So of course it has a square. All right. So it does have a. So when I ask you what's the von Mises stress, don't forget to put the square root on. Okay. So that's the definition of von Mises stress. Okay. All right. Yep. So that's pretty much it. Right. So you just decide which one to use, and to simply put, pretty much most of the time we'll be using distortion energy, because von Mises stress is a very powerful quantity we can use, because one, it's easy to get. That's what the finite element gives us, right? Second, we have this criteria here, which is fully based on von Mises stress. You just compare that von Mises stress with the yield strength, and that's your criteria, right?
What do you mean by being aggressive or conservative with your design? Like,
Oh.
Are you taking into account a lot more things that can have stress, or you being like lax about some stuff?
Yeah. So when I say conservative or aggressive means, for example, when you design a structure, right, you have maximum stress in the material, right? So, for example, the stress state is like in point B, all right? You have certain number of sigma A, you have certain number of sigma B. So I'm going to decide whether it's going to be failure or not. Then if you use maximum shear stress, at this point, it tells you failure is going to happen. But if you use distortion energy, it's going to tell you, you're still fine, right? So in reality, we want to, of course, we have design safety factor to take into consideration of safety. But if you use maximum shear stress, it's going to be more conservative. So you have to make sure your stress is inside this envelope, then failure is not happening. Make sense? In other words, okay, here's a good example. In other words, if you drive on a Texas highway, as long as you don't exceed 80 miles per hour, you're fine, right? Speed limit is 80. If you drive to New Mexico or you drive to Arizona, then the highway is 75. That tells you if you drive 80, you're already speeding. Make sense? So distortion energy is a Texas highway. Maximum shear stress is New Mexico highway. Get it? Right? If you drive 80, you're fine in Texas, but you're not fine in New Mexico. Get it?
Yeah, I guess it depends on what risk you want to take. If you want to make it really safe, or
right. Yeah, sure, you can say that. Yes, if you want to make extra safe, then use maximum shear stress. Okay, but here's the interesting thing, because like I said, this is for tensile. No. Ductile. There's lots of ductile material. Alloys, right? Aluminum, or even you can say plastic is ductile material, right? Lots of ductile material here. Now, they did a bunch of testing. Depends on different two-axis loadings. They fall in line here. Some of them falls in between. Some of them falls in between, inside of the maximum shear stress. So really, I'm not saying one is better than the other. Depends on the material, all right? So back to the fundamental. Depends on whether you want to be conservative or you want to be aggressive, right? Make sense? Yes. All right, but since maximum shear stress is, it's very hard to predict, and I don't think the finite element can tell you the maximum shear stress, whatever, different case. But finite element can easily tell you the von Mises stress, which is a, where is it? Where did I write it? Up? Okay, here. Since a finite element can tell you this, so try to use distortion energy, which is accurate enough, because don't forget we have the design safety factor, right? Okay. Let's see here. Okay, I don't think I'll have time to go through example today, so let me just finish it up, and on Thursday we'll go through a big example. Okay. To cover all the maximum shear stress and distortion energy criteria. Okay, now remember there's a flaw for distortion energy. What's a flaw? We only consider normal stress, right? In reality, you have shear stress as well. So you have this, right? Or if we put in red, you have shear stress as well. So to be one step further, shear stress looks like this. So for For 3D case, for 3-dimensional loading, sigma prime equal to square root 2 x minus y, y minus z, z minus x plus 6 tau xy, tau y z, tau zx square root. So when I use sigma prime, it means I'm calculating the vomitive stress. All right. Okay, so also we have a 2D case. Sigma prime is nothing but equal to sigma x, xy, and y plus 3 times tau xy square root. All right. Yep. So that's what we're considering here. That's all the things about distortional energy. Let's do one more thing. We still have 10 minutes, right? All right. So what if you have pure shear stress? Pure shear stress. Now, don't forget, for vomitive stress or for the distortion energy, we are comparing this. This is our criteria, right? If your vomitive stress is equal to SY, that's a critical point for failure to happen, right? Okay. So if you have pure shear, in other words, X, Y are all 0. All you have is your shear stress. So for pure shear stress, vomitive stress is just equal to tau xy square root. And if that equal to SY, that's my critical point, right? All right, so what you have is to the square root on both sides, divide by 3 on both sides, and then you have this. Therefore, tau xy is equal to roughly SY divided by square root of 3 equal to 0.577. That's right. Why it's important? Because sometimes you have pure shear loadings, right? Once you have a pure shear loadings, then you can use the tensile yield strength to design to guide your designs. As long as your shear stress is not, I guess iPad is tired, huh? Class is over. Come on. It tells you. There you go. It tells you when the shear stress is equal to about 57.7% of tensile yield, tensile strength, then failure is going to happen, right? So as you can see, distortion energy tells you it's a distortion causes failure. Of course, when you have shear stress, you cause more distortion because all shear stress does is distortion, right? But for tensile or compression, you still have the hydrostatic component and distortional component. Make sense? All right. So, yes. All right. Somewhat. Okay. It's all right. I'll try to go through an example on Thursday, and hopefully that'll help you to understand it better. Okay. All right. I'll see you guys on Thursday.